The year 1938 marked a pivotal moment in astrophysics, a year when Subrahmanyan, Chandrasekhar, a name now synonymous with the rigorous application of theoretical physics for astronomical phenomena, published a seminal paper. The work, Stellar Configurations with Degenerate Cores, represented more than a mere contribution to the burgeoning field. It offered a profound and, at times, controversial re-evaluation of the fundamental principles governing stellar evolution. To fully appreciate the significance of this paper, one must first delve into the intellectual landscape that Chandrasekhar navigated, a landscape shaped by groundbreaking discoveries, fierce debates, and the ever-present quest to understand the cosmos. The stage was set by the relentless progress in both theoretical and observational astronomy. The early decades of the 20th century witnessed a paradigm shift in our understanding of stellar structure and evolution. The quantum revolution, with its introduction of concepts like electron degeneracy, had a direct impact on the theoretical frameworks used to describe the behavior of matter under extreme conditions. This, in turn, challenged classical models that proved inadequate in explaining the observed properties of white dwarf stars, objects of immense density and peculiar behavior. Prior to Chandrasekhar's work, the scientific community grappled with explaining the observed properties of these stars and the ultimate fate of stellar objects. Central to this problem was understanding how stars resisted their own gravitational collapse. The key factor was believed to be atomic nuclei and their resistance to gravitational pressure. Chandrasekhar, drawing upon the work of Arthur Eddington, Ralph Fowler, and Wolfgang Pauli, approached this problem using the emerging principles of quantum mechanics. Eddington, in particular, championed the idea that radiation pressure played a dominant role in the structure of stars, an idea later refined to include the role of gas pressure. Fowler, building on the work of Pauli in 1926, first elucidated the concept of degenerate electron gas within stars. He recognized that, at extremely high densities, electrons can no longer occupy lower energy states, a consequence of the Pauli exclusion principle, which states that two or more identical fermions cannot occupy the same quantum state within a quantum system simultaneously. This principle provided a powerful counterforce against gravitational collapse. Chandrasekhar, armed with these insights, aimed to expand on Fowler's work and to address the complex interplay of gravity, electron degeneracy, stellar structure in greater detail than ever. In Stellar Configurations with Degenerate Cores, Chandrasekhar meticulously explore the structure of stars with cores composed of degenerate electrons, a state of matter previously considered solely in the context of white dwarf stars. Chandrasekhar's work introduced a detailed mathematical model, incorporating relativistic effects for the first time in a comprehensive stellar structure calculation. He developed a rigorous framework based on the equations of stellar equilibrium, using these equations to derive a limiting mass for white dwarfs. He demonstrated that, beyond a specific mass limit, called the Chandrasekhar limit, the electron degeneracy pressure is insufficient to counteract the gravitational attraction. In this work, he presented a model of how to solve the Lane-Imden equation, which describes the pressure of a star in hydrostatic equilibrium as a function of its radius. For the specific case of a degenerate core, the equation, presented in full in the paper, included the effects of general relativity at the time. This limit, a critical value of approximately 1.4 solar masses, represented a profound prediction that any star exceeding this limit would inevitably collapse, ultimately forming a black hole or undergoing some other catastrophic event. He demonstrated that stars which were already white dwarfs, hence in the degenerate configuration, could eventually be pushed below a critical minimum radius, resulting in the paper's immediate impact was substantial. It provided a theoretical explanation for the observed properties of white dwarfs and predicted a critical mass that divided the stable white dwarfs from the stars and would inevitably collapse. This represented a crucial step forward in our understanding of stellar evolution, offering an endpoint to the life cycle of stars and matched observational data. Chandrasekhar's work provided a theoretical foundation for the study of stellar remnants. His prediction of a maximum white dwarf mass quickly gained traction within the astronomical community, allowing them to refine their observations and theoretical models. His use of the Lane-Imden equation, when combined with the Chandrasekhar limit, became a standard tool for astrophysicists. The paper's influence quickly extended beyond the immediate context of white dwarf stars. The concept of electron degeneracy and the associated limit became fundamental to comprehending the evolution of various celestial objects. The work also played a crucial role in the development of the theory of neutron stars. The discovery of neutron stars several decades later, objects of even greater density than white dwarfs, confirmed the theoretical models put forward by Chandrasekhar and offered further empirical evidence for the validity of his groundbreaking work. His calculations of the mass-radius relationship for very dense objects, which included considerations of relativistic effects, became a cornerstone of the theory of compact objects. The reception of Chandrasekhar's work was complex, marked by both acclaim and resistance. Initially, The paper faced skepticism, particularly from established figures like Eddington. Eddington, a leading authority on stellar structure, initially dismissed Chandrasekhar's theory primarily due to the counterintuitive result of a mass limit. This rejection, fueled by Eddington's own views about the role of radiation pressure and the stability of stellar configurations, created a period of considerable professional tension. The intellectual debates, characterized by sharp disagreements and sometimes personal animosity, served to slow the acceptance of Chandrasekhar's insights. The scientific community, including Chandrasekhar himself, later addressed the disagreements. While the initial reception contained some aversity, Chandrasekhar's rigor and persistence in formulating his arguments eventually led to a wider acceptance of his insight. Chandrasekhar's later work, and the broader developments in astrophysics, also shaped his paper's enduring legacy. The paper's impact on subsequent research has been immense. It influenced the development of several related fields, including the study of supernova, binary star systems, and the evolution of massive stars. The Chandrasekhar limit became a fundamental building block for understanding the life cycle of stars. It is now used to determine the fate of any given star, based on its initial mass. This is a tool that is widely applied in astrophysics to this day. It provides a criterion to determine when a star will eventually collapse. The theory has been refined over the years, expanding from the original framework to better address the effects of rotation, magnetic fields, and other variables. But the central premise, the basic tools by which astrophysicists approach the question, remain as Chandrasekhar laid them out in 1930. Several individuals directly influenced the genesis of stellar configurations, with Degenerate cores. The work of Arthur Eddington, as previously mentioned, was crucial in the understanding of stellar structure, especially the role of radiation pressure. Ralph Fowler's work on degenerate matter provided a key building block for Chandrasekhar's work. He built on earlier theoretical works by Max Planck, Albert Einstein, and Satyendranath Bose, further developing the foundations of quantum theory. Furthermore, the early contributions of Wolfgang Pauli, including the formulation of the Pauli exclusion principle, were essential. Chandrasekhar himself acknowledged the intellectual debt he owed to these scientists, recognizing that his work was built upon the foundation they had carefully laid. The impact of Chandrasekhar's work extended far beyond the initial paper itself. His work directly influenced generations of theoretical astrophysicists. It led to a deeper understanding of the different stages of stellar evolution. Several scientists were directly influenced. Physicist and astrophysicist Lev Landau, building on Chandrasekhar's work, developed an understanding of neutron stars. This, in turn, influenced other scientists. These individuals included J. Robert Oppenheimer, who applied Chandrasekhar's ideas to the study of the ultimate fate of massive stars, and George Gamow, who incorporated the Chandrasekhar limit into his theories about the formation of elements in the universe. These are only a few examples among a long list. In conclusion, stellar configurations with degenerate cores represents a landmark achievement in astrophysics. It provided a fresh lens through which we could see the lives and deaths of stars. Chandrasekhar's work, with its rigorous mathematical approach and insightful predictions, transformed our understanding of fundamental forces in the universe. The paper not only explained the properties of white dwarfs but also paved the way for the deeper study of the cosmos. The lasting influence of Chandrasekhar's work lies in its profound impact on the intellectual trajectory of astrophysics. The concept of the Chandrasekhar limit remains a critical tool for astronomers today. The paper's legacy lies not only in its original scientific achievements but also in the inspiration it provided the succeeding generations of scientists. The work stands as a monumental testament to the power of theoretical physics and its ability to illuminate the grand mysteries of the universe. The legacy continues,